the quantum dot cellular automata by expert Dr. Dipti Kurgewadi, followed by that the hands-on session on QCL Designer tool. We will end this day in our last day with the MCQs, feedbacks, and lots of interactions. We are looking forward to lots of interactions with you all in this coming 6 days, and we'll end this FDP with a valedictory session on the last day. So that's all that we have for you for this coming 6 days. Before we begin, just few requests and instructions to all the participants. Attendance is mandatory for all of us for these 6 days. That will ensure that we get the utmost benefit out of this FDP. Not just that, we'll be having a feedback link that will be shared with you at the end of every session. You all are requested to fill that feedback form positively. We provide, through the ATAL, we provide travel allowances to faculties who are coming from a distance which is beyond 20 kilometers. So please ensure you keep your receipts and share with us from time to time, so that will enable us to help you all with that. Lots of instructions I will be discussing from time to time during the 6 days. So I think it's a good time to start my first session. Okay, so now I invite Mr. Jeevan from Corel Technologies. He's an application engineer at Corel with his expertise in Verilog, C and Python. Not just that, he has expertise in FPGA tools like Vivido Design Suite, which includes IDP Integrator, Vivido Simulator and Vivido Logic Analyzer. He also would like to have lots of experience in mental graphics, front-end and back-end design tools, including Tanner.
Welcome to all the professors and all the English students who are presenting. So firstly, I would like to introduce myself. I am Jeevan Pierce. Basically, I am from Bangalore. I am working as an application engineer over 1+ years of experience in Korean technology. So before Korean Technologies, I was working in the Machina Semiconductors as an application engineer for the embedded parts. So after that, I switched to the Korean Technologies. So we'll start this session with the front-end design using Vivido Design. So we are going to see what are all the front-end flows includes and how the Vivido will support the front end and how the back end will be done in the Vivido design. So same as the AICTE designs, but in the AICTE designs we are going to do all your customizable floor planning and I/O planning. But here, when it comes to the Vivido, the back end part will be taken care of the Vivido itself. So we are going with that flow and we are going with the Vivido flow and we are comparing with the Vivido flow of an front-end design with the hands-on experience. Okay. So before moving to the technical session, I would like to introduce about my company portfolio. So we are into system engineering and engineering technology solutions company. So we are into defense and aerospace and digital video broadcast and high performance computing and higher education markets. So these are all the fields we are working with. So we will have the different departments in our company. One is research and development team and design and verification team and EDA team who are working with the scientists in ISRO and DRDO, and the UPD team where in the UPD team we are working with the professors and PhD students and research projects like that. So we are there world-class product development capabilities where we are working with the defense and ISRO for their projects, and we have recognized by the DRDO one of the finest R&D of the electronic product development team, and we recognized as a world-leading developer of most dense and complex design implementation in the FPGA. So when it comes to the engineering solution, avionics and missile electronics, RF system and solutions, high performance computing, video solution, and COTS boards. So when it comes to the avionics and missile electronics, we are into integrated avionic modules, Seeker processing units, and off-board computers, and RF system and solutions, which undercomes transmitter receiver modules. Recently we have even the tracking receiver radar system for the ISRO for the Chandrayaan 3 project. and exciter and receivers, GN based SSPs. And when it comes to the high performance computing, PAM, pulse amplitude modulation board based high speed NIC, and 6x100G NIC. And when it comes to the video solutions, imaging processing unit for submarines, flying point tracking system for anti-drone systems, and H.264 decoder, and video format converters. And COTS boards are single board computers of Power PC or Intel, and Gen 3 RF subboards, zinc ultra scaleless boards, and zinc boards. So these are all the engineering solutions. So we bring in OEM technologies, and we bring in Sandeepani Institute of Embedded System Design, and these are all our alliances. So when it comes to the OEM technology solutions, we have supply of system designs and analysis and manufacturing, software consulting training and implementation to defense and space and enterprise companies. And we set up some of Center of Excellence and Higher Education Institutes in Engineering. And when it comes to the Sandeepani Institute of Embedded System Design, this is a training division in OEM technologies where we are giving the internship for the students like BE, BTech and ME, MTech. And this is the authorized training partner for Xilinx in India and Sri Lanka. Advanced VLSI design and embedded system courses will be provided. And when it comes to the mechanical engineering, mechanical designs, analysis and manufacturing training will be provided. And system design and analysis. And our alliances are Mentor Graphics and MathWorks, ANSYS, Siemens, AICTE Xilinx, and QT and downstream technology and building. So I would like to introduce about the Sandeepani. This is a pioneer in BLS and embedded system training in India. 4 years set up the Sandeepani to bridge industrial and academic gap of students. And this Sandeepani is associated with OEMs like Xilinx, Mentor Graphics, Siemens, and ANSYS. And who are all the faculties, they are giving training for the students and the ISRO scientists. Those all faculties are Xilinx certified faculties. And by enrolling or registering to this Sandeepani, you will be getting access for the high quality materials, labs, and EDA tools. And faculty experience with a giving training for the entry-level engineers. And we train over 10,000 plus professionals from various industries, academicians, and students for HDS, FPGAs, verifications, and system designs. Our customers for the Sandeepani enrolling or registering like startups, independent design houses, captive MNCs design centers, defense and aerospace companies, and universities and institutions. These are all our customers who are going to enroll the courses or any customized training for their necessities. And our special project when it comes to an education part, special manpower development project implementation in VLSI and embedded system for MBTI phase 1, 2 and 3. And Siemens Center of Excellence at NIT Kurukshetra, Siemens Center of Excellence at AICTE Jodhpur for Electric Vehicle Research, and Siemens Center of Excellence at IIT Goa, and ANSYS Center of Excellence at Bharat Electronics Bangalore. These are all the special projects when it comes to the education side. And we do have value-added reselling portfolio, Mentor Graphics, MathWorks, ANSYS, and Siemens. So when it comes to the Mentor Graphics, we are having a bundle-wise tools which including IC design and verification and high-speed PCB design, signal and power integrity, and safety critical FPGA designs and verification. So however, all the institutes and engineering colleges will be having the leading companies. They are procuring the IC nanometer designing tools with cadence or with the Mentor Graphics. So one of the best advantage compared to the cadence is the Mentor Graphics tools who are all working. The Mentor Graphics are working with the professionals, and this Mentor Graphics using by the students, professors, and mainly this Mentor Graphics is using in ISRO and DRDO for their research purpose and for the manufacturing lead. And we are having MathWorks, which can design, simulate, and test automated driving systems. We can design, code, and verify embedded systems. And ANSYS, this is for the mechanical tool, where they can do structural analysis, computational fluid dynamics, electromagnetic high frequency simulations. And we will have Siemens reselling portfolio, that is with virtual product design, validation and optimization, product engineering, process optimization, and knowledge-based creation, and manufacturing process design and validation. So this is one set of reselling portfolio, and this is the next reselling portfolio. Next set, QT, Wind River, Downstream, and Xilinx. Today we are going to use AMD Xilinx. So all we do have know already. Xilinx is acquired by AMD. Right? So now it's AMD Xilinx. So we are quality of ISO certified 9001 certified company. Now let us start with the technical session of today's FPGA design, which we are using the front end design. So this is how the course flows like. Once we completing this session, you will be able to understand describing the general FPGA architecture, understanding the viewer flow, create and debug the RTL code, verifying the functionality of design, and utilizing the available resources in the synthesis and implementation stage. And we are going to utilize, we are getting the report of utilization resource, how much we use, and the power resources and time resources. And we are going to configure the FPGA verify hardware operations, and we are going to create and apply I/O and timing constraints. And we are going to identify the different sets of files like HDL, XDC, and simulation file. And we are going to analyze the design by using cross-protein selection and capabilities and schematic viewer and hierarchical. So this is the first session course outline, where we are going to see about the 7 series architecture overview and understanding the flow of front end and back end in FPGA by using viewer design. And we are using verification design flow and synthesizing a RTL design and hands-on using hardware and verifying the functionality of the design. This is of first section. This is of the second session outline. Implementation and static timing analysis, where time requirement and requirement which needs to meet the designs. So all will comes under the static timing analysis. And IP integrator, why we have to use IP, and we are going to explore the IP catalog. What is the purchase, how the purchase IP looks like, and how the free IP looks like, how we can package the IPs, how we can available that IPs in the viewer. And Xilinx design constraint and hardware debug. This is all about the session 2. So this is the prerequisites, the basic HDL knowledge on HDL or Verilog, any one of them, and digital design knowledge and experience of the hardware. So this is the platform support for the viewer design suite. XUP, Xilinx University Program Boards, PCC3, PCCET Zygo. In this today's session we are going to use. And these are all the supported operating system for the viewer design suite. So I'm going to talk about the 7 series architecture from now. Before 7 series, we all know Spartan 3, Spartan 5 series were introduced. After that, we introduced the 7 series architecture. We got to support only from the starting of 7 series. It starts from the 7 series. We can support the Spartan 3 because that is very later course. So that's why we support from the 7 series. So 7 series, 7000 zinc FPGA boards. After 7 series, there will come ultra scale. After ultra scale plus boards. Right? we'll see now the introduction of Xilinx 7 series FPGA. So whatever all the FPGAs you will see in the 7 series or ultra scale plus, all those resources will be same as you look like it. Logic resources, interconnect resources, and other resources. In other resources where global clock buffers and boundary scan logic will be included. So when it comes to slices, it grouped into a configuration logic blocks. So where in the slices you will be having slice L and slice M. Where slice L mean to be only logic, it is not going to store any data in the slice. And where slice M mean to be distributed, it acts as a distributed memory and also it acts as a shift register. So when it comes to slice L, it is only mean to the logic. It is not going to store any data. So this is grouped into a CLB, configuration logic block. This CLB is made of 4 components. That is, one is LUTs, and another one is flip-flops, and the third one is full adder, and fourth one is multiplexer. By including these are the 4 major components, by using these 4, this CLB has been made. We are going to see these slices of slice L and slice M, and also inside CLB I told you 4 components were presented in the CLBs. We are going to see the implementation stage while we are using the practical session. So next one is memory. We are having 2 types of memory, that is DRAM and VRAM, distributed RAM and block RAM. Where this distributed RAM logic LUTs can be implemented in the SRAM blocks in the distributed memory. And when it comes to the VRAM, the LUTs are implemented for the dedicated SRAMs, where the difference between DRAM and VRAM in the logic resources is, in the DRAM they don't have any reserved VRAMs, so any reserved SRAMs, but when it comes to the VRAM, it have the reserved SRAMs where the VRAM implementation can be done. Understand, this is the difference between DRAM and VRAM in the memory block of logic resources. And the last one is multipliers, where we are doing the arithmetical operations and multiple of multiplications operations, where at that stage it is going to make a parallel execution in the logic resources part. This is all about the logic resources. Then I am getting into the interconnect resources, where we are having programmable interconnect IOPs. This programmable interconnects where the input and output from the PS to PL part will be connecting to extend the input output peripherals, and the IOPs input output blocks where the interfaces between the FPGA, and it helps to connect for the outside world by using different type of sensors or actuators or like P modes, GPS, Wi-Fi, like those things. We are having other resources where global clock buffers and boundary scan logic. So when it comes to the global clock buffers, the global clock buffers will be inside integrated with the FPGA, where this is responsible to supply the whole circuit, to supply the clock for the whole circuit. That will the global clock buffer also called as clock buffers, because this clock buffers is responsible to send the clocks for all over FPGA design. Whatever all the circuits integrated in the FPGA, the clock will be supplied from the global clock buffer, where the 7 series FPGA boards having onboard clock which will be a 100 megahertz, right? Onboard chip. And boundary scan logic. This boundary scan logic is used for to scan the input interconnects or input wires or input connection that made from one part to the another part, and the output same like the inputs and clocks. All the input output clocks will be scanned by the boundary scan logic. So So this is all about the introduction for the 7 series FPGA design. If you have any doubts, you can stop me at that point, or you can just note the slide number and the question if you may ask later. So this is the 7 series architecture alignment. What are all the 7 series FPGAs? This will be a alignment looks like. This is the arrangement of CLBs, configuration logic blocks, DRAMs, input outputs, clock management tiles, CMP, FIFO logic, and DSP buffers and IO, buffer input output, and regional buffers. This is the overview of how the architecture alignments looks like. So in 7 series, these are all the different families which will be comes under 7 series FPGAs. Then ATIC 7, INTEC 7, Vertex 7, and Zinc. So ATIC 7, this is the lowest power and low cost. When it comes to the INTEC 7, this is the industry best price and performance will be good. And the Vertex 7 is upgrade version of the INTEC, where the industry highest system performance. When you need the high performance for your projects, for that purpose the Vertex 7 will be used. And Zinc. These three ATIC 7, INTEC 7, and Vertex 7, these three are FPGAs. And Zinc is also FPGA, but this is the system object where the PS part will be included. In ATIC 7, INTEC 7, Vertex 7, in these families, these are all not system object. Means the PS part will be not present in these three FPGAs. But to extend the processing system, to extend the IO peripherals, they invented the processing system part, PS and PL. PS for the processing system and PL for the programmable logic. So you can observe here, from one family to the another family, the resources are increasing, are incrementing. You may observe in logic cells, where in the ATIC 7 they are having 20K cells and 355K cells, and when it comes to the INTEC 7, 70K to 480K, and when it comes to industry's highest system performance, that is Vertex 7, this will be having 285K to 2000K. But when it comes to Zinc, this is lesser than the INTEC 7 and Vertex 7. This is 30K to 350K, because here they invented PS as well as PL part. That's why the input, the logic cells will be lesser compared to the INTEC 7 and Vertex 7. Right? Same like logic cells, the block RAMs, DSP slices, and DSP preference and transceivers, these all will be implemented from one family to the another family. The basic family or the basic FPGA is low-ended FPGA is ATIC 7. From the ATIC 7, before ATIC 7, the FPGA family is Spartan. So after Spartan, ATIC 7, INTEC 7, Vertex, and Zinc. So this 7 series FPGA is 28 nanometer technology. Okay. So in ultra scale, you will be getting INTEC 7, Vertex 7, and Zinc. ATIC 7 will be not presented in ultra scale. Okay, and that ultra scale boards are 20 nanometer technology. And when it comes to the ultra scale plus, you will be having Vertex and Zinc. Only these two families will be presented in the ultra scale plus series, where ultra scale plus series is of 16 nanometer technology. Right, after that, the now the latest one is Versal ACAP, that is of 6 nanometer technology. And we can observe here all the 7 series FPGAs having, they will be requiring only the same input output voltages, 3.3 voltage or below, like 1.8 voltage to the 3.3 voltage. So the voltage, input output voltage will be same for all the FPGA families. So this is of different FPGA families. So now we understand what are the different series are there, 7 series, and after Zinc 7 series, we are having Zinc Ultra Scale. After Zinc Ultra Scale plus. of the ultra scale plus versal area with the 6 nanometer, right? From the 28 nanometer to 20, 20 nanometer to 16, 16 nanometer to 6 nanometer. This is all about the 7 series FPGA families. So now we are going to see the Zinc 7000 chip. We are not going to see RTX 7 Intex or Vertex. We are directly going to the Zinc. So what is meant by Zinc? So it's having PL part along with the PS part, okay, which is connected to the ARM to extend the input outputs for the processor, okay, for the extending of input outputs like UART or USB or HDMI, like those input output peripherals, you can extend the PS part by accessing the PL part. This interconnected way from using the ARM cortex. So are having two series, RA, RR. Okay, here we are using RA9 dual processor. So it's having RA and RR processor, two different series. A is for application, R is for real time. So if you are selecting the AP, which application processing unit for your application, you are not going to do any real time project, then you are going to select the A series, where in the Zinc you will be having. In the ultra scale plus, you will be having MP SOC, means multi-processor system on chip. You are having multiple processors, like 3 to 4 processors you will be having. Those are APU, GPU, RPU and VU. Means application processing unit, real-time processing unit, graphical processing unit, video coding unit. These 4 processors will come under 7 ultra scale plus, means Zinc 7, Zinc MP SOC, is multi-processor system on chip. There they are using ARM Cortex A series and ARM Cortex R series, both, because real-time applications you will be using in the ultra scale plus, and also A94 will be used in APU, application processing unit. So now we will see about the highlights of the Zinc 7000 families. Mainly it divided into 3 parts. First is APU, and another one is tightly integrated programmable logic, that is PL part, and flexible array of IOs. Okay, this is complete ARM based processing system. Told you APU is a dual ARM Cortex A9 processor, A meant by the application, R meant for the real time. So it's having dual ARM Cortex A9 processors, which having 32-bit, and it's having the caches and support blocks, L1 caches and L2 caches. We'll go depth on L1 and L2 in the next upcoming slides. And it's having fully integrated memory controllers, like static memory controller like Quad SPI, NAND, NOR, and dynamic memory controller like DDR3, DDR2 and LPDDR3. And we are having IO peripherals in the PS part processing systems like SPI, I2C, CAN, UART, GPIO. And we are having the second one is tightly integrated programmable logic, where it used to extend the processing system. Right? Here we are seeing 3 different colors. One is blue, light green, another one is yellow, and another one is light green. So here, whatever all the highlighted yellow part, that is all about the PL part, programmable logic. And whatever all the light green part, that is the APU unit, where the application processing unit, processors block diagram. And this grey part is of PS part, processing system part. So here, this programmable logic is used to extend the processing system. Means here this will be programmable logic is connected from here to processing system. and from here to the processing system. So PL can access the SPI, I2C, all the IO peripherals can be accessed by the PL by interconnecting to the PS part. So scalable density and performance. It's having multi-standard IOs, which will be a 54 input output you will be getting from the programmable logic to interconnect for the processing system. And when it comes to the flexible array IOs, you will be getting wide range of IOs, like you can see here, multi-standard IOs. This comes under the flexible array of input outputs, and you are having high performance integrated serial transceiver, which is the multi-gigabit transceivers, and analog to digital converter inputs. This is the XADC. Xilinx analog to digital converter. This will be a on-chip XADC. You can use for any conversion of analog to digital conversion ports. So now we are going depth on the high overview of the 7 series architecture. First, I'll just start with the APU. Here, they are using dual ARM Cortex A9. They are using the Neon FPU engine. FPU is for the floating point unit. Why they are use the FPU engine? Because this FPU will do the parallel processing instructions. Okay, that's why they use the FPU engine, because this is the system on chip where it's having PS and PL both the parts. So the design of the circuits will be complex. The implementation will be densely used. Like they are using the bulk amount of input-output cells. They are using bulk amount of DSP slices. They will be using bulk amount of logic cells, LUTs like that. So for that purpose, they use FPU because it want to do the parallel execution for the quick implementation. And here in the Cortex A9 MP4, it's having input instruction catching and data catching, where that is of 32 KB of instruction catching and data catching. Where instruction is responsible to give the instruction for the ARM Cortex, and data cache is responsible to store the data and to stream the Cortex A9 processor's data. And here we are having L2 caching. This is of 512 KB, where it stores only the necessary data of Cortex A9 data. And Snoop control unit SCU. This plays an important role because this is going to this is responsible for if any changes have been happened in the Cortex or in the L2 caches. Those updated information or updated signals will be updated by the SCU, Snoop control unit. This is responsible to monitor the updated one or whether the updated data is updated or not. If the updated data is detected by the Snoop control unit, it is going to update the data in Cortex A9 as well as the L2 cache. And we are having the timers and counters, and on chip 256 KB. We are having general interrupt controllers, DMA configurations, where DMA is going to send the direct access for the master slaves, where you are having 2 GP port, that is AXI general purpose 0 and 1, and master AXI general purpose 0 and 1. You will be having 2 ports for the slaves and the masters. You will be having different 2 ports, 2 vessels for the slaves and as well as masters. This is all about the APU. Now I am moving to the programmable logic. Here you will be having the 4 HP, means high performance ports. These all ports, what you are seeing, these all are slaves. So the last one is ACP, that is the accelerator coherency port. This is directly connected to the APU. This provides the asynchronous caching coherently from PL to the APU unit. And these all HP0, HP1, HP2, HP3 is connected with the APU. This you are using for the high performance of interconnecting for the AICTE ports. And after this, we are having the processing system part. This they invented to exchange the input outputs, where you will be interacting or you will be sending the data, or you are going to transmit or receive the data by using this extended peripherals like SPI, I2C, GAP. From UI you can send the data, transmit and receive the same data. GPIO, SPIO with EMA and USB with EMA and ATAL with EMA. This is all about the 7 series architecture. So this is about the Xilinx FPGA evolution. Firstly, they invented the ATAL, which having only the PL part, programmable logic. After that, they invented the processing system in the Zen. That they are having PL part as well as PS part. And after that, they got one scenario where the customers or the developers needs more processing system, means more processors, multi-processors they need for the image processing, video processing, or graphical units for the graphics processing units, or for the real-time applications. We want these all in the single FPGA. For that purpose, they extended the processing systems. They are having the multi-processors in the Zinc MP-soft. That is MP-soft means multi-processor system on chip. Okay, this is how the evolution started from FPGA. After FPGA to Zinc, Zinc to Zinc Ultrascale. Okay, where you will be requiring only the FPGA, means programmable logic part. Then you are going with the FPGA like ARTIC 7, KTEX 7, Vertex 7. If you want some more processing system and some large amount of PL part, programmable logic part, then you will be going with the Zinc. When you want more of PS part and some less amount of PL part, then you will be going with the Zinc MP-soft. Okay, this is all about the evolution of FPGAs. Now I am entering to the front end and back end design. So by using Ecodo, first we are going to take the specification of requirement of the customers, whether what is the clock and what time it needs to be made, what should be the timing requirement, and what are the input and outputs that required in this design. So all these specifications we are going to take, how much temperature within this circuit need to be done, and how much power this system need to be done, or any design is to be done. Because if some designs uses the more power, then it will be waste. Then they will ask, we need less power compared to this. This is more high power. For that purpose, we all access this. We can see the utilization of these power resources and the input-output resources, clock networks, how much clock we are using. These all we can take the reports by using the Ecodo. So first we are getting these all data as a specifications, right? After that we are going to the design entry. So first in the design entry we are writing the code in the HDL, whether it is Verilog, VHDL or system Verilog. After that we are going to do the behavioral simulation. First stage after the design entry we are going for the behavioral simulation. Where in the behavioral simulation we are going to check the behavior of the circuit or behavior of the code as whether it's working as our intent or not. So if it is not working, again we can directly quickly go for the design entry, means for the code, and we can change. So what if they put it, or if they invented that behavioral simulation after implementation? So one disadvantage is that is a time kill process. So once the implementation has been done, after that we are going to see the behavior of the code that is not at all good for any of the designers. So that's why they keep behavioral simulation in the first. After behavioral simulation check is finished, my Verilog code is done. I am done with the Verilog code. My Verilog code is working fine as our intent. Next I am going to the constraints. Constraints means you will be having the XDC file, Xilinx design constraint file.
which having all the input output pins to be accessed from the board. All the system on chip input output pins will be there. Those all information will be stored in the XTC file. That is called as master XTC file. That is the master for that particular board which you are using. If you are using the basis 3 master XTC. If you are using Nexus A7 board, Nexus A7 master XTC file. These are all the files where these files consisting of all the input output clocks and P modes, counters, 7 segments, all the information of the boards will be having in the constant file that you are going to access, and you are going to give the constants in the XTC file, right? After giving constants, so I return the program for Verilog code, means for the design entry, and I return the code for the constants, means for the functionality, to check the functionality of the hardware. We are done with these two things. Next, I am going to the synthesis, where we need to check how much, what are the netlist created from that design entries, and what are the input output cells, or what are all the instances and entities that design entry having. This will be done after the constant file, after the behavioral simulation. After the synthesis is done, the next step is this is translating the net list to the place and route for the optimization. Okay, so I will tell you in the upcoming slides what the synthesis does, what operation technically synthesis does. Before synthesis, there is a called RTL analysis. In RTL analysis, technically what happening after RTL analysis, in synthesis what is happening, after synthesis in implementation what is happening. So for those happening process, what are all the required from the design entries? We are going to discuss in the next slide. So after this, we are going to check the functional simulation and static timing analysis in the synthesis stage. Okay, where in the static timing analysis, all the reports of timing requirement that meets the timing requirement or not, these reports will be taken to the static timing analysis. So in the functional simulation, we are going to see the functions of the synthesis. Once the synthesis is finished, after the behavioral simulation, we will be getting the post-functional simulation reports. There we are going to verify the functional of the code. If that is not intending as per our intent, then we are going to modify the design. Or otherwise, we are going to the next stage, that is the implementation stage. In the implementation stage, optimization, placement and routing will be done in the implementation stage. So once the placement and routing has been done, I will get the reports. We will get the reports in synthesis stage also, after synthesis, and we will get the reports after implementation also. But we will get the reports synthesis also, implementation also. That is also. But what's the difference between the reports of generated synthesis report and implementation report? Any idea? So in synthesis stage, we will be having the estimation of the input output utilization. Only the estimation. That is not the final one. We will get the estimation of the reports. But once the implementation has been done, we will get the exact utilizing resources and the reports of timings and the reports of the cost. Because in implementation, the placement and routing will be done here. So once the placement and routing has been done, no alternative you are going to do. No changes you are going to do. So once the implementation has been done, whatever all the reports you get, that is the final report. But when it comes to synthesis, whatever all the reports you get, that is not the final one, because that is just the estimation. Okay, this circuit will consume this much of this circuit will consume this much of logic cells, LUTs. Just it will give the estimation. So once the place and routing has been done, the next one is we are going to generate the bitstream file, where this bitstream file having the information of the report that generated from the implementation. Whatever all the implementation reports done, after that it is going to put in the bitstream file. This bitstream file is readable from the FPGA code. This file will be taken out to check the functionality of the code. So we are putting that generated bitstream file to the FPGA board, then we are going to check the functionality. So in this, the backend works starts from the implementation stage. Here, after synthesis in the implementation stage, IO planning, load planning, timing analysis, all will be done in the implementation stage. So in the ASIC designs compared to FPGA, you are going to give all the you are by own yourself you are going to do the IO planning and flow planning. But when it comes to the Vivado, you don't want to do the IO planning or flow planning. By taking the constant file as an input, it will do the IO planning and flow planning. Because all the input output plannings you are going to give the input output in the constant file itself. That's why you don't need any alteration. If you want to do alteration, you can also do in the IO planning. But as we recommend, the tools will be by taking all the scenarios, by taking all the references from the constant file, it will do its best performance. It will do its best IO planning and IO flow planning. So any doubt here? So this is all about front end and back end. The back end starts from implementation, where the implementation stage you will be having placement routing. In placement routing, you will be having IO planning and load planning and timing analysis. So let's start with the Vivado design flow. You just try to compare the front end and back end design with Vivado. So this is the design database. Each process operates on a netlist and will modify the netlist or create a new netlist. Once this will be a different process, design process. From first, it will do the elaborated design, next synthesize, and its implementation. For these all three steps, you should have the netlist. That netlist will be created from the Vivado. It is created by taking input as you return the HDL code. That HDL code will take the HDL code and it will compile the HDL code. Then it will do the netlist. It will list the netlist and it will give the netlist for elaborate and synthesis and implementation. For those three steps also, netlist is very important. As by taking netlist only, it is going to do all the process. Placement, routing, optimization, synthesis, schematics, all will be done by taking the netlist. So, once the synthesis has been done, we will get the netlist optimization. Once the netlist optimization done, then it will do the power optimization. Once the power optimization done, it will take to the placement. After placement, it will take physical optimization. After physical optimization, routing. Routing is the last step. So these all database includes in the Vivado design. So in Vivado IDE solution, we are having interactive design and analysis, RTL development and analysis, and X simulation, simulator integration, synthesis and implementation in one package, and IO
From the starting first, you can get that.
Software exports.
Yes.
See?
Okay, just go to that location. Like the file.